Hi everyone, and welcome to another episode of Organic Chemistry with Wikipedia. Today we're going to be talking about the properties and polymerization of unsaturated hydrocarbons. So let's get started. All right, so first up, where do alkenes come from? So alkenes are present in nature. We especially deal with ethylene and propylene for commercial use. Ethylene is created from the thermal cracking of ethane, which is you take it and you put it in a heater for a super long time. So what happens here is we take some ethane, CH3, and we heat it up, and this produces two CH3 radicals, which are not stable. Radicals are substances that only have like a random floating electron here. So this is a highly unstable substance. So one of these radicals then immediately reacts with another ethane molecule. And this produces a CH4, so our radical is no longer unstable, and it instead produces this other radical that is slightly more stable because it is a longer chain. Now we can take this radical and this radical will then react with, that's not a radical. So that radical then reacts to create a more stable CH2 double bond CH2 and a hydrogen radical. And then hydrogen radicals will react with other hydrogen radicals to then produce hydrogen gas. Hooray and huzzah. So when we add all of that together, what we basically get is that some ethane in the presence of heat reacts to give you ethene or ethylene and some hydrogen gas. So that is the cracking process. Excellent. Hey. All right, alkynes, where do alkynes come from? Alkynes are not really present in nature a lot, and there's not really a lot of application of alkynes in organic chemistry or in biochemistry, so we don't really talk about anything to do with them. So alkynes are getting put on the shelf. They are all alkynes of sad because we're not using them. Fun jokes. Okay, so general properties of these, they are nonpolar. Because they're nonpolar, the intermolecular forces they exhibit are the London dispersion forces. Melting and boiling points, therefore, follow the same patterns as alkanes. Because alkanes only have single bonds, their melting points are not going to be as high as alkenes that have double bonds, and they're going to be lower than alkynes that have triple bonds, just because of the intermolecular forces that are involved there, so that trend kind of follows that. Liquids usually have densities less than 1 gram per milliliter, so they float on top of water, which they are insoluble in, but they're soluble in a variety of organic solvents. Okay, there is a very specific type of alkene. It's a diene that we call a terpene. That is, so our terpenes here have one double bond. They're separated, the double bonds are separated by one carbon. So this here is a terpene molecule. This is called isoprene. Let me rephrase. So this is called, this specific type of terpene is created from linking isoprene units together. And these guys right here, these are our isoprene units. The actual name for the isoprene unit is 2-methyl 1,3-butadiene. And so this is, but it's more often called isoprene. So when you take terpene units and link them together, when you take isoprene units and link them together, you make terpenes. All right, so here we have the way in which they link together doesn't really matter, but there's a couple different formations that we can have. So when you link them, the formula that all of them have is C5H8 to the N, where N is the number of double bonds that you have. So it can, or the number of isoprene units that you have. So that's the general formula of our terpene here. So we can have what's called a head-to-head link where the two double bonds combine together. Well, the two double bonds are always going to combine together, but like where you have the double bond is closest to the methyl group, those two combine together. Here you have the double bond closer to the methyl group and the double bond farther away from the methyl group. There's nothing here. Combine together, and that's a head-to-tail link. And then if they're both the double bonds that are away from the methyl groups, then those are tail-to-tail links. So the head of this is where the methyl group attaches, which you can kind of sort of see, because like if you flip this, it looks like this, where you have that and then you have that. So it kind of like, this is like the little head of a person. And then they have, I guess, like two arms on one side and none on the other side, but to each their own. All right. So because this is a double bond here, the double bonds can create stereoisomers. So the maximum number of stereoisomers you can have is 2 to the n power, where n is the number of double bonds that are present. So here's a couple of different examples of what happens when you link them together. So here we have a head-to-tail linkage here, and this creates something called myrcene. Here we have a couple different ones that are linked together to produce retinol. Retinol is a really important terpene because it is the stuff that enables your eyes to see. Retinol is what combines with something called opsin to produce a cis isomer. And then when your eyes receive light signals, the light causes it to turn into the trans isomer, and that trans isomer is what signals to your brain that you are seeing something. So literally the only reason why you were able to process and intake light is because of cis-trans isomers. So that's a bit of a fun fact. And then here we also have, like, you can have the linkage actually occur to create a ring. This is limonene, which is exactly what it sounds like. It smells like lemons. All right, so these are different types of terpenes that we have here. Terpenes are really important because they can combine together to create polymers. So we can have enzyme catalyzed reactions to create polymers out of terpenes and other things. Like it's the creation of terpenes is kind of what led the way into the creation of polymerization. And polymerization is very, very important for us because it's where plastic comes from. And so it's not necessarily, like a good important or a bad important. It's just important because currently our world is overpopulated with plastic, and we don't really have any really good ways of destroying it. So however you think of it, it's still important. Okay, so excuse me. All right, so let's talk about polymers. All right, so the most important reactions of alkenes are the formation of what are called growth chain polymers. So the presence of certain compounds that we're just going to call initiators. We're not going to get into the actual mechanisms of what the initiators do and how they make it work. But we're just going to call them initiators. And what happens is when you put these alkanes together, they form these long bonds they form these long chains of repeating alkene units. So these long chains are called polymers that are made up of individual monomers. And so to name a polymer, you just add the word poly to the front of whatever the monomer unit is. So for example, if we take ethene or ethylene, that is not ethylene, this is ethylene. All right, and then it undergoes, so we have n number of ethene monomers. And so here we take an initiator. And what we do is we create a polymer, and the polymers are written in this fashion. So we have this, like that, and then it's to the N. So what that means is that we break apart this double bond and we just create this giant chain of CH2 molecules. And so there's a double bond that is in between each of these monomer units. So we've got, if we look at this, kind of if I draw this out for you, we have that and, oh, no, sorry, they're not single bonds. I don't know why I said that. They're still double bonded. My bad. There we go. All right, and so we've got that, and then that, and then, yeah, I'm just trying to use it correctly. All right, and then they just kind of go on forever and ever and ever, and then there's just like an H and an H that comes off of here that are from the original initiator. So we can just sort of create, like, they keep building on top of each other, building on top of each other, building on top of each other, and like we're talking about ends in the thousands. So that is the basic way in which we create polymers. So common polymers are the monomers. They come from the monomer unit. So if we use ethylene, this is where we get polyethylene, polyethene, all of these things. If we take propylene and we make polypropylene, and then some other ones that are really common are if you have chlorine, the chlorine units make really good ones. So you have this ethylene, and so you get this polydichloroethylene, and then we can see here that we've got some other things, and they get more and more complex as we go along. So let's talk a little bit about each of our little polymers here. So if we have polypropylene, so propylene just looks like this. And so if we take n number of propylene, we add an initiator, and to this it actually opens up the double bond here. So what ends up happening is you get this here. And so this looks like CH2, CH2, and then it actually opens up CH3 here. And then we just have a little bond that goes there to the end. So this is polypropylene. Another really popular one is what's called polyvinyl chloride, which is, it looks like propylene, but it is actually, instead of a methyl group here, you have a chlorine group. So this creates, with an initiator, this guy here to the N, and that is some polyvinyl chloride, which is just a PVC. So if you've ever used PVC pipe, that is what you are using, polyvinyl chloride. I'll write this here, vinyl chloride. Okie dokie. And then we have, so our more common polyethylene is comes in two different forms. We have what's called a low density polyethylene and then the high density polyethylene. So for low density polyethylene, the initiator that we use is peroxide at very, very high temperatures, so 500 degrees Celsius, and then also very high pressures, over 1,000 ATM. So it's super, super heated and pressurized, and it creates a very, very branched polyethylene. So like the actual isomer itself is super, super branched. So it creates, I'm doing this right, like this. And so it creates just this like very, very, very branched. And so we can have this come off of here. And it keeps kind of, I don't need to have this here. So it kind of keeps going in all directions. And so because it's creating such a branched chain, it's low density because the chain takes up so much space that the amount of mass per volume is very, very high. Sorry, very low. It takes up a lot of volume and not a lot of mass, and so it's considered to be low density. The low density stuff is what we use for like plastic wrap and trash bags and things like that, are all low density polyethylene. And then high density polyethylene was discovered much later using the Ziegler-Natta method. And if you take organic chemistry in college, you will talk much more about this. during that time. This was really great because you didn't have to have a peroxide initiator, and you got a lot of straight chained polymers here. So you ended up with, that is not anything, this is just this. So you ended up with a lot of straight chains, and because the chains are straight, they have the ability to stack on top of themselves more. And so they are high density because now you have a whole lot of mass in that same volume as we were looking at before. You can have many, many more chains, and so this is high density. This is a much stronger polyethylene. It's used for things like milk jugs and plastic lawn furniture. So like if you have those like plastic chairs that you keep outside, those are made out of this high density polyethylene, probably using the Ziegler-Natta method. So fun stuff. So under recycling, this is just a fun little fact here. All of your recycling codes are based on the types of things that we are using here. And that's why like it's important to separate your plastics out, because they are made out of different types of polymers. And so because they're different types of polymers, they require different methods to kind of, for lack of a better word, melt them down and start over again. So this is just kind of gives you an idea of all of the different types of recycling kind of stuff that we have. All right, so that is properties and polymerization. This has been another episode of Chemistry with Wikipedia, Organic Edition. I hope you learned something, and until next time, keep on chemin'.